In this video, we're going to talk about the reducing agent DIBALH, Diisobutyl Aluminum Hydride. That will be a single hydride donor that we specifically pair with esters in the hopes of obtaining an aldehyde. Now, before we get into that, let's backtrack for a second and remind ourselves that when we paired an ester with lithium aluminum hydride, there was a 2 times reduction of the carbonyl carbon. The mechanism proceeded through an aldehyde intermediate, but we could not stop at the aldehyde there. The aldehyde would continue to react with lithium aluminum hydride. So if our hope was to actually convert an ester into an aldehyde, we would not use LiAlH4, right? We would use DIBALH, Diisobutyl Aluminum Hydride, which can also be written as IBU2ALH, Diisobutyl Aluminum Hydride. Notice we're going to do this reaction at a cold temperature, and we only need a 1 equivalent amount of DIBALH, 1-to-1 ratio. Check this out. Mechanistically, the carbonyl oxygen first complexes with the aluminum that charges the aluminum negatively. We will then observe an intramolecular hydride addition. That breaks the pi bond, generating this tetrahedral structure. And as we're keeping this cold, we can essentially ensure that that tetrahedral structure does not collapse and kick out our OR leaving group, forming an aldehyde intermediate, essentially because of the sterics involved and associated with the isobutyl groups. And the fact that we're keeping this reaction cold, we can ensure that all of our ester reacts with all of our DIBALH to produce this gangly-looking tetrahedral structure. Okay, I'll repeat that. All of the DIBALH reacts with all of the ester to produce this tetrahedral structure here. And so in your mixture, you'd have a bunch of these structures at the end of step 1. Then when we do H3O+, it's not just a workup step per se. There's a little bit more going on. When we introduce that structure to H3O+, we're going to break the aluminum to oxygen bond and form an OH group. Now, specifically, that's a hemiacetal. We have an OH and an OR group bonded to the same carbon. And under the conditions of aqueous acid, we're going to have that hemiacetal equilibrate to an aldehyde. Mechanistically, the OR component here of our former ester will protonate. We protonate that OR group, making that definitively the best leaving group in the tetrahedral structure, and then our oxygen of our OH group will collapse, kicking out an alcohol leaving group. That's ultimately our alcohol byproduct. And then finally, we deprotonate the aldehyde intermediate at the carbonyl oxygen, forming our aldehyde product. So think about H3O+ as breaking apart the tetrahedral structure, creating a hemiacetal intermediate, and then that hemiacetal equilibrates to form an aldehyde. The net result is, visually, we slice and dice our ester, but we reduce once and get an aldehyde. Okay? DIBALH, Diisobutyl Aluminum Hydride. Doubtful that you'll have to know the mechanism for this reaction, but I find it's helpful to show the mechanism just to validate everything. Okay, just to repeat the conceptual details. DIBALH stands for Diisobutyl Aluminum Hydride. That's a sterically hindered single hydride donor. We only need 1 equivalent of DIBALH for every 1 equivalent of ester. And we react at a cold temperature. We react at a cold temperature to ensure that there's no collapse of the tetrahedral intermediate. Then in step 2, when we add our water in, we break apart the oxygen to aluminum connection point, forming the hemiacetal, and then that equilibrates under acidic conditions, kicking out the OR component as an alcohol leaving group. And we net result generate our aldehyde, and of course then have our alcohol byproduct. Reduction with DIBALH.